Hello and welcome. In this video, we're going to take a look at a neat little application of integral calculus, some statistics, and demographics. We're going to be taking a look at Lorenz curves and the Gini index. And what this does is it gives us some sort of representation about the equality of the distribution of wealth in any given population. So we'll have to collect some statistics on that first, and then a Lorenz curve helps us to model that information, and a Gini index gives us some sort of description about how equal or unequal that distribution is. So let's start off with a Lorenz curve. This is a model of income distribution of a population. And it's a function, so let's denote that function L of x. And L of x tells us what proportion of the total income of that population the poorest x percentage receive. So maybe let's think about how this would be set up with a set of axes and how we might graph this. Now the horizontal axis here, x, that's the poorest x percentage of the population. As a percentage, it can only go as high as 100%, represented by 1. So at a x value of 0.5, that would be the separation of the poorest 50% of the population on the left and the most wealthy 50% of population on the right-hand side. Now we may want to divide this up into either quartiles or deciles, for instance. And that will represent the entire population now from 0 to 1. Along the vertical axis, this is what proportion of the total income that percentage of the population is receiving. And this is cumulative. So, we should be starting off with, if we have 0% of the population, we'll have 0% of the total income. And if we have 100% of the total population, then the proportion of that income would be 100%. So the vertical axis really doesn't need to go any higher than 1 for 100%. 100% of the population will have 100% of the total income. So it's a function that connects the points 0, 0, and 1, 1. We can't just have any function connecting 0, 0, and 1, 1. There are several properties for Lorenz curves that they must obey. We already know that the domain needs to be from 0 to 1 inclusive, and the range need to be from 0 to 1. We also already know that L of 0 equals 0 and L of 1 equals 1. But now we also have to have a fact that this function needs to be non-decreasing. That means that the first derivative of our Lorenz curve needs to be greater than or equal to 0. Every time that we include more individuals, and as we move further along to the right along the x-axis, the total income cannot decrease since we're only going to be including more individuals. It's possible that income can remain constant or increase, but we can't be decreasing. What might not be quite as obvious is that our Lorenz curve either is concave up or linear. It can never be concave down. That means that the second derivative of our function is always greater than or equal to 0. So it's going to be sort of accelerating upwards. We know that if we had more wealthy people at the top end of our spectrum, then we're going to imagine that income is going to be increasing more quickly towards higher values of x and more slowly towards lower values of x. It's possible for this to be increasing rapidly for the poorest x percentage and slower for the more wealthy x percentage. So it's always going to be concave up or possibly linear. Last but not least, another property is that the value of L of x is always less than or equal to x. This is because the poorest, say 40% of the population, cannot possibly have more than 40% of the total income. Even if everybody had exactly the same income, the poorest 40% of the population would be making the same as everybody else and therefore would only have as much as 40% of the total income. So with all of those restrictions in place, you can kind of get a sense of what a Lorenz curve probably looks like. It's always increasing or linear and concave up, and it's always going to lie below the diagonal line, potentially equal to the diagonal line. Here's a good example of a Lorenz curve. By putting some scales on the left-hand side, this vertical axis is the proportion of total income. And so now you can maybe see that the poorest 50% of the population, maybe they're only getting 25% of the total income. Now take a look at the 9th decile, that's the 90th percentile. They're making 75% of the total income. So by the time we've included 90% of the population, we're still only getting 75% of all of the income. That would imply that this remaining 10% from the 90th percentile to the 100th percentile, they're actually getting 25% of the total income. Gives you kind of a sense as this is not a very equal distribution. If you wanted perfect equality, though, then X% of the population gets X% of the income. That would be represented by a perfectly diagonal line passing from 0, 0 to 1, 1. That red line is a Lorenz curve. It does satisfy all of these criteria. It's non-decreasing, it's concave up or linear, and L of x is equal to x, which is allowed. This is perfect equality. This gives us a bit of an idea of a description of how unequal a particular population's distribution of wealth is. We will compare our Lorenz curve to that perfect diagonal line. Now the equation of that diagonal line could just be y equals x, or L of x equals x. If we want to determine how far away from perfect equality we are cumulatively across the whole population, then what we can do is calculate this shaded region between perfect inequality and any given Lorenz curve. Using our method for area between curves, we will look at the definite integral from 0 to 1, which is the entire population from 0% all the way up to 100%. And we will take a look at the difference between perfect equality, which is the Lorenz curve L of x equals x, and our given Lorenz curve L of x. Now using this integral, we will always end up with a positive value because our Lorenz curve is always going to be less than or equal to that perfect equality line. But this value is also always going to be less than or equal to 1/2, which is the total area of the triangle underneath that perfect equality. Since we're not quite satisfied with this value ranging from 0 to 1/2, what we've decided to do is double that particular area, and we call that the Gini Index. By doubling the value of this integral, the Gini Index is a value from 0 to 1. If the Gini Index is equal to 0, then the area between perfect equality and our Lorenz curve is 0, and therefore we have perfect distribution of wealth, or total equality. But if the Gini Index is equal to 1, then that means that the area between the perfect equality line and the Lorenz curve is equal to 1/2. That would be a pretty strange looking Lorenz curve. That would mean that 99.9999% of the population all have 0 income, and only the one person at the end here has a whole 100% of the income. That's perfect inequality, and that's the only way that we could have a Gini index equal to 1. Now, with the Lorenz curve, the units along the x-axis are percentage, the units along the vertical axis are percentage, so the area here is unitless. These are simply just proportions times proportions for area. The Gini index is this great unitless number from 0 to 1, so it's a great scale to use to describe inequality or distributions of wealth. Now, let's see if we can take a look at an example. Now, the tricky part with this integral formula is actually coming up with the equation of a Lorenz curve. It's pretty straightforward by some sort of census data that we can get a distribution of income. We might record what percentage of the total income each percentile or decile of the population is receiving. That, unfortunately, is discrete data. So we might say that the poorest 10% of the population have 5% of the wealth. The poorest 20% of the population have 10% of the total wealth, that kind of thing. We can get that information, but trying to turn that into a smooth curve that we can integrate can be a little bit tricky. So there are several different theoretical models for Lorenz curves that we could use. Let's start off with a simple one. For a very basic example of a Lorenz curve, we could say that L of x is some function of the form b minus a over b times x squared plus a over b times x, where b can be any positive number and a is a value between 0 and b. We can double check by plugging in 0, that L of 0 equals 0, so that criteria is obeyed. We can also check by plugging in x equals 1 that we end up with b minus a over b plus a over b, which is equal to b over b, and that's equal to 1, so that criteria is obeyed. By taking a look at the derivative of this function, since a and b are always positive, we can see that this derivative is always positive. We can also check concavity by looking at the second derivative of this function. We'll see that that's always positive as well. So it's obeying all of the major criteria. And we also recognize that this is going to be a parabolic shape and therefore is curving upwards and is always going to be less than that diagonal line. Here's an example. Here are two Lorenz curves using that particular model. 14 over 15x squared plus 1 over 15x. And 19 over 20x squared plus 1 over 20x. In both cases, a is equal to 1. In one example, b is equal to 15, and in the other, b is equal to 20. And without having to graph these two functions, we can check what the Gini index is for each of these populations and see which of the two populations may have more inequality than the other. Now, it's important to remember when using the formula for the Gini index to use parentheses here. When we integrate x minus our Lorenz curve, we want to make sure that we subtract every one of the terms in our Lorenz curve model. So x minus 14 over 15x squared and minus 1 over 15x. We can distribute that negative sign and collect terms. Distributing and collecting terms, you can see that we have a common factor of 14 over 15 in our first example and a common factor of 19 over 20 in our second example. Pulling out these common factors and multiplying by the 2 in front of the integral, we can actually see that they both end up with the definite integral from 0 to 1 of x minus x squared. And that's just a simple power rule. The antiderivative, 1/2 x squared minus 1/3 x cubed, and then we will evaluate from 0 to 1. And plugging 1 in, we'll have 1/2 minus 1/3, which is 1/6. Plugging in 0, we'll have 0. And it may help to actually evaluate these as a decimal, since we know that this value should be between 0 and 1, and we might want to see roughly whereabouts on that scale each of these Gini indices are. This gives Gini indices of 0.311 and 0.317. So it's a very minute difference between the two. But knowing that the Gini index of population B is a little bit larger, that would indicate that this population has a larger amount of inequality. This is a very basic model for a Lorenz curve. Let's take a look and see how well this model might actually be able to model real data. So let's take a look at Desmos here. And in the blue and green dots here, I have actual data from the Canadian distribution of wealth in 1990 and in 2009. You might be able to take a guess as to which is which. Here, this blue model is 1990. And you can see that the green model below that, the green data points, well, that's the distribution in 2009. And it's getting less equal. As you can see, these dots are moving away from the perfect equality line. Now here, this red line right now, you can see is the perfect equality model. But it's actually the function up here. L of x equals b minus a over b, x squared, plus a over b, x, graphed from 0 to 1. That's our Lorenz curve model. And here I've got two sliders for A and B. So we can actually see if this is a realistic model that will somehow fit these data points. B is equal to 1 right now, and A is equal to 1. So right away, if you see B minus A over B, that's just 0. This is the line L of x equals x. But if we increase B, you can see what's happening to this model. Well, it is getting a little bit closer, but not very close. It's getting better and better, but I'm going to have to let B be an extremely large number to get even close to those values. Changing A will actually bring us closer and closer back to a straight line again. A can be between 0 and B. So, this model has its limitations. I might have to choose an extremely large value of B to even get close to these values. We can improve upon this model a little bit. Rather than having this be forced to be x squared, we might change this maybe to x to the power n. Now I've got an additional slider bar here, and this is with n equal to 2, and that'll be the same model that we currently have, and you can see that we have those limitations. But by changing this from a quadratic function to maybe a cubic, we might be able to get a little better. You can see that this is actually getting fairly close to those blue dots now. Maybe a quartic is closer to the model. Well, maybe that's even getting worse. Yep, doesn't look like it's helping very much. We might be able to adjust some values here, but I'm having a real tough time making this model fit that data. So there might be something that's a little bit more intricate than simply just a polynomial x to the n plus x with these two coefficients that add to 1. Now you can take a look at all kinds of research for maybe finding a better Lorenz curve model. Here's another model, and we have 1 minus w1 over 1 plus w2, and that's being multiplied by another fraction, 1 plus w2x times x over 1 minus w1 times x. w1 and w2, again, are these parameters that we can adjust to try to make this model fit the data. Now, originally in the paper that I found this model, this was using omega, but Desmos doesn't really treat Greek letters as friendly. So why don't we go ahead and see how this model fits our data? You can see that adjusting one of the parameters, w1, this is something between 0 and 1. That seems to really make a huge difference. It's not just changing the degree of a polynomial now. You can see that this is becoming almost asymptotic near the end here. So we can get a real good bend in our Lorenz curve. Let's see what happens with the other parameter. Well, that seems to sort of adjust, especially the very beginning behavior of our Lorenz curve. Between the two of these parameters, we might be able to sort of fit that data relatively well. And it takes quite a lot of playing with it, but you can try to get through those blue dots and you can see relatively what the Lorenz curve model might look like for the Canadian distribution income in 1990. And again, if you want to go to 2009, then this becomes a little less equal, and we can maybe adjust that a little bit to try to get a better model there. So there's interesting research to be done on what might be a very useful Lorenz curve model. This particular model has 2 parameters. It may be useful to have a Lorenz curve that has 4 parameters, perhaps. You can go ahead and take a look at some research on different models for distribution wealth. Now, just to note that when you're actually calculating the Gini index in maybe a more practical circumstance, rather than trying to come up with a Lorenz curve model that fits the data, you might end up actually just calculating it with discrete points. You could just go ahead and really just add up the different deciles, for instance, 10%, 20%, 30%, 40%, and really approximate this area just using rectangles. And you can get that directly from the data. If you wanted to maybe be a little bit more precise or a little bit more mathematical, I guess, then you can really start investigating these different Lorenz curve models and properly calculate the area under that curve. And that may give you a smoother representation of the population and maybe a more realistic Gini index. Well, there you go. That really ties together some mathematics and some statistics. First of all, you need to have the data. You have to be able to actually collect enough information to get an understanding of what the distribution of wealth looks like. Those data points, for instance, were just from Statistics Canada, and that was free information, so you can download that yourself. With those points, then you can get a little bit more into the mathematical world of how we can model that data with a smooth distribution function, and then we use integral calculus to be able to calculate something that comes back and describes the population. That's our Gini index. So there's a lot going on there. Thanks for watching, and I'll see you in the next video.